Okay, so in this video we're going to talk about some applications of integration to physics. We've already talked a little bit about the fact that you can calculate work done by a variable force by integration. In this video I'm going to try to explain to you how we can calculate the force on a dam, due to pressure from the water. And the thing that makes it complicated is that the pressure varies with depth. All right, so let's get into it. The other application we'll talk about is the so-called centroid or center of mass calculation. Should mention that the center of mass centroid calculation can be more properly understood in the context of a complete course in physics, but I'll show you the formulas here nonetheless. All right. Anyway, eventually. So if P with a foot, big P, if you like, is the pressure, that means it's the force per unit area. So if we think about a little dA, we can think about the little force dF, and that's the pressure. Infinitesimal force dF over infinitesimal area dA is give me pressure. So to calculate the net force in some region R due to a force F from some sort of gas or liquid, we simply find dF is pdA, and then we integrate over the region the integral of pdA. Now this kind of integral we can often set up a la calculus 2 style in terms of a one-dimensional integral. All right. For more complicated geometries, you might need methods of calculus 3, but here calculus 2 will do just fine. All right, so the water deeper down pushes more forcefully on a dam than the water near surface. However, the water at fixed depth pushes in a uniform fashion. Here's the way it works. So it's an experimentally determined fact, what I'm saying, that the water at a fixed depth pushes in a uniform fashion, right? And the reason for that, of course, is that the pressure in the water is based on how much water is stacked on top of that water. And for a given depth, we have the same amount of water above the water. Something like that. Anyway, here it is. Pressure is the density of water times acceleration due to gravity times depth. This is the experimentally determined pressure as a function of depth. This is depth below the surface, of course. This can be rewritten as delta D, where delta is the weight density. I think this is sometimes called the specific density, if I remember right. It's 62.5 pounds per feet cubed, units which pretty much only live on in calculus books. I much prefer 1,000 kilograms per cubic meter times 9.8 meters per second squared. This is the SI unit way of thinking about it. Anyway, these equations make sense in part because the density of water is independent of the depth. Perhaps this is a bit surprising. Contrast in the equations for a gas in the atmosphere, they would not have this feature. Air is less dense at high altitudes. That would be a more complicated problem that I at one point in my life have discussed in a physics course, but this is not a physics course, so we're going to focus on pressure and force on a dam due to water. Here we go. So one, and we'll start with an example actually, the hydrostatic force on the window in the aquarium pictured below. So we want to find the force of the water pushing on this little window as sketched. All right, 3 feet, 8 feet, 2 feet. So it's 3 feet below the water, and then 8 feet, and then 2 feet like that. Now, if you're not a fan of calculus, and you're just like, it should be just like it's. Well, I'm not gonna say. There's a way to do this without calculus, but I'm gonna shut up about that. Here's the way to do it properly with the infinitesimal methods that I'm trying to teach you. Here they go. So we choose coordinates which are natural. Be sure to define them with pictures or words. So here's my picture. Y equals 11's up here. I'm going to put y equal to 0 at the bottom of the window we're trying to find the force on. And I'm going to think about a little dA right there, because I want to find the force due to that, due to the water pressing on just that little infinitesimal area. The reason I want to look at the horizontal strip is because the pressure is constant along a given depth. So I can calculate the force on this strip by just focusing in on that. we need to work out dA and the pressure in terms of the coordinates which are given. We need to express the depth and to calculate the pressure correctly. So here, the dA is 2 dy because we had 2 feet. I'm going to zoom out just a little bit in the interest of getting a little bit more of my analysis in one slide. I hope you can still see everything. I don't think that's going to make my words too small for you, but I just want a little bit more of the picture in there at once. So, so you need to express the depth of D and calculate P correctly, as I was saying. So because this is 2, the dA is just 2 dy. The depth D is, and you see if this is 8 and that's 3, this makes, if this is 0 down here, that makes that 11, right? 8 plus 3 is 11. So I have that y plus d is 11, which means that d is equal to 11 minus y. All right. So the little bit of force on that strip is PdA, or delta dA, delta dDA if you like. Anyway, so I guess I went with the delta because it's less writing. Delta d is 11 minus y, the dA is 2 dy. This is from 0 to 8, right? We can imagine drawing this little strip from y equals 0 all the way up to y equals to 8. That's where the window is. That's where I need to sum over to calculate the net force. So we find the hydrostatic force is given by that integral. We do the integral, and we find 112 delta. It's slightly out of my window. Let me scroll up a bit here. We find 112 delta. Delta is 62.5, so that gives us 7,000. At this point, I put the pounds back in. It's okay to work in this, at least as far as, if you're in my section anyway, I would hope. Well, anyway, I mean, not cast aspersion on those who are more careful than I am, but I just, to reduce clutter, I do not put units in such calculations. I'm just careful to make sure to use consistently scaled things. I don't mix inches with feet. I don't mix miles with meters, but here all of the given data was in terms of feet, and the delta is in terms of pounds and such. So this ends up giving me a force of 7,000 pounds. Now the answer, we should be careful to supply units, right? So, like, I know, imagine you're on the job and your employer asks you how much carpet you need for the new building or something, and you tell them you need 7,000 square units. And you're like, he's like, 7,000 square units of what? And you're like, I know, it's just 7,000 square somethings. He's not going to be happy with you, right? I mean, units matter. You're like, I'm not planning on designing or accounting for the amount of carpeting in some new building. Well, fine, but you pick up the example which is relevant to you. Units matter. So anyway, when we're omitting units, beware of multipliers and consistently presented data, inconsistently presented data, like inches versus feet. In a science course, such as physics, you might be expected to manifest. That means make them clear, like in your face. Units in both calculations and in answers, but here I'll just insist on in answers. All right, moving on. Let's look at something a little bit tougher. Find the force on the aquarium window pictured in terms of constants L, H, rho, and G. Ooh. So here's the surface of water, and I've got this triangular window like so, and I'm asked to calculate the hydrostatic force on the window. So here's how we do it. We introduce coordinates and a picture. We draw a picture to introduce the coordinates. Is what we do. I set up the dA, which again is from a horizontal strip because that's where the pressure is constant, so I can logically calculate the dF like so. And so dA is W dy, whatever this width is. I'm just giving a label. W dy is the dA. Here W is a linear function because the slope is, it's a constant slope there. And in fact, I would point out over here that w is a linear function of y. That's pretty clear, since we want w to be equal to L when y equals to 0, and we want w to be equal to 0 when y is equal to h. That gives us 2 points on the line, and that suggests that we write w is equal to L minus L over h times y. Now, if you don't believe me, you can check. We plug in 0, we get L. We plug in h is canceled, we get L minus L, which is 0. All right. Now, what I didn't write down here is that, like, to actually work that out, I didn't show you the algebra that was done there, but it's basically this. Just if we decide w is linear, that means that w of y is equal to, let's see here, I need some letters. Let's say my. I don't think I've used b anywhere, so let's say my plus b. So we got like y of 0 is equal to m times 0 plus b, which is equal to L. And we got w of h is mh plus b, which is equal to 0. So this one, since 0 times m is 0, this tells me that b is equal to L. And then this tells me that m is equal to minus b over h, which, by the way, is minus L over h. So therefore, w of y is equal to, well, minus L over h times y plus L. That's the right formula for the width as a function of y. And that is what I wrote down here to start with, okay? Anyway, setup aside, let's continue on here. So my dA is w dy, which is this. This one's a little bit more interesting because the dA is a function of y, right? It's biggest down here and it's 0 up there. dF is pressure times dA, which this time the depth is equal to what? It's equal to h minus y, right? And so we get dF is rho g L, rho g d, I put the d over here, and this is actually from the dA. It's the L times, I factored out the L here, L times 1 minus y over h. And this is going to be the case between 0 and h. We're going to have a little bit of force on each horizontal strip. To get the net force, we add up the force on each horizontal strip all the way from top to the bottom, or from the bottom to the top, I should say. And we do that by taking the continuous sum, which is the integral. By the way, that's why this is like an S. It's for sum, continuous sum. Anyway, I hope you don't accept proofs by notation that much, but it's not really a legitimate method of argument. All right, anyway, so we do this integral, and I won't belabor the details here, but it works out to 1/3 rho GL h squared, like so. So there you go. Next up here, a little bit harder. Find the force on a half circular window. Depth h below the water, like so. Give answer in terms of rho, g, h, and r. All right, here we go. So again, we're going to have to divide this up into horizontal strips and calculate the dF on each one as a function of like depth. We'll have to invent a coordinate system to make this make sense. So first order of business, draw a picture, choose coordinates. I put y equal to 0 down here. And I put the origin right there to make life easier, because then at least this we know the equation of. It's x squared plus y squared equals to r squared. And so then this point would be a point on the circle x comma y. But we can solve for y. It's the square root of r squared. Oh, wait a minute. Rather, hold on a second. dA is 2x dy. Ooh, I was being smarter. All right, so if this is x, then this is 2x, right? And dy, so 2x dy is the dA. Oh, but I'm going to do an integration over y here, right? So I need to solve for x as a function of y, which is easy enough to do. R squared minus y squared equals x squared. Take the square root. I get that. I keep the positive square root because I'm thinking of this point right here being the x. And that's why I'm going to integrate from 0 to r, because I'm integrating 0 up to r like that. All right, the pressure is rho g, and how did I get that? Rho gd. I said h plus r minus y. Why would that be? Let's see here. Well, let's see here. H is the distance from here to here. R is the distance from there to there, so r plus h is up here. And I said that the distance from here to here is h plus r minus y. That makes sense because, did I write it down somewhere? I didn't write it down anywhere, but the reason for that is just simply that y plus d is equal to h plus r, right? So if y plus d is equal to h plus r, if we solve for d, we get h plus r minus y. Anyway, do make sure you understand this. If you don't understand it yet, draw yourself some pictures and stop and make sure you understand that before you go on. All right, so there's the depth. All right, so rho dA, pressure times dA is the force on the strip, which in terms of everything we just worked out is that. So I've got to integrate that thing from 0 to r, but we know how to do that because it's either like a plain U substitution or a trig substitution. Anyway, we have all the necessary mathematics to calculate that integral. So I do it. I do something a little bit sneaky here, actually. Let's see here. So what I do, I put the y over here. I put h plus r. I factored it out. I have this right here. At this point, I was like, wait a minute. You know what this is? This is twice. This is 2 times the integral of the square root of r squared minus y squared dy. Think about that in terms of area. That's the area of a circle. So this just integrates to pi r squared, actually. And I said pi r squared over 2 because, because I'm only integrating from 0 to r. If you think through it, that's just half the area of a circle. And then there's still got the rho g h plus r out here. And on the other hand, this is a u substitution. Don't forget, we've got to change the bounds. If y is equal to 0 and u is equal to that, that means that u of 0 is r squared. On the other hand, if I put r equal to y, I get r squared minus r squared, which is 0, so u of r is 0. So when I change the integration from y to u, the bounds change from 0 to r squared and from r to 0. All right, then integrate, get that, evaluate, there you go. So, there's a lot of the integration we've so far learned or trying to learn this semester, all working together in concert to solve a kind of interesting problem. Of course, you could calculate this directly by a trig substitution, but I just chose to recognize it as an area to shortcut some work. Next up, center of mass and moments of about the origin. So in this case, we're going to change the meaning of rho now. So sorry. So rho in physics is often the mass per unit area. All right. Actually, delta, sometimes sigma. I usually would use sigma for mass per unit area personally, but anyway, let's say rho is mass per unit area. And the mass area density, so that means dm is rho dA. So if I want to calculate the total mass in the region, I just integrate rho over dA. Then the center of mass is given by the, well, I'd say weighted averages, but these aren't weights, they're masses. Sorry, it's a horrible joke. But anyway, center of mass, x bar, y bar, is given by this. 1 over the total mass, integrate x times the density. And 1 over the total mass, integrate y times the density. So this is mx, this is my. These are the moments in the x and y directions, respectively. In particular, basically, we just have x bar as mx over m and y bar as my over m. So to find the center of mass, we need to calculate m sub x, and m sub y. And if you got those 3 things, you can calculate the center of mass. In contrast, the centroid is the center of mass if we take the density to be equal to 1. You can also say the centroid of a region is sort of the geometric center. All right. So in that case, if we take the density to be 1, then the total mass is just the area of the region. In fact, if the density is constant, then the center of mass is in the same location as the centroid. But if the mass was not of constant density, if the density was variable, then the centroid and the center of mass could be different places. A little bit more in terms of formulas here. If we have the region as being between A and B and between two graphs, y equals g of x is the lower graph and y equals f of x is the upper graph, then the mass we could integrate density times f of x minus g of x dx, because this is just the formula for dA. Here I'll draw the picture. Let me draw the picture. So A, B, you got some lower function g. You've got some upper function f. All right. And so you want to calculate the net mass of that thing. So what you got to do is chop it into pieces, right? And if you were to think about, I don't know, the, say, mass of this little strip right here at x, right? The thickness would be dx, the dA would be f of x minus g of x, because that's the height of the strip, right? And so dm would be, well, the density times dA, right? In this case would be the density times f of x minus g of x dx. And that's why we have this formula up here. It's, again, arising from the infinitesimal method, if you want me to keep selling that to you. Now, in contrast, the x moment and the y moment are given by these formulas right here, and this really involves the particle concept from physics. I better not explain it here. All right, anyway. So this is to calculate the x and the y. We also come to a better explanation in Calculus 3. I'm not going to try to explain it here. For us at the moment, it's just a formula, but the centroid is the geometric center, the center of mass is the balance point. All right, so let's actually calculate a couple of these. I gotta get a new cover sheet here. I keep writing on my cover sheet and it gets cluttered. So find the centroid of the region bounded by y equals x squared and x equal to y squared. All right, so this is what that looks like. So we're looking at that. And so we have x squared less than y less than the square root of x. The area is this, which is equal to 1/3, which is the mass in our thinking, because the centroid we just put density equal to 1, so we can think of the area as being the mass, so to speak. The x moment is integral of x times that, which works out to 3/20. The y moment, we take 1/2 f of x minus g of x squared. F of x squared is square root of x squared. G of x squared is actually going to work out to x to the 4th. And we integrate those, and we also get 3/20. So by symmetry of the region, we could have claimed this to start with anyway. I mean, you can kind of see that if I did a better job graphing that, these are really symmetrical in the sense that of the way they curve and so forth. So it makes sense that the center of mass should be on the line y equals x, but it's in fact at 3/20. So, oh wait a minute, I can't do math. I've forgotten. We have to divide by m to find the actual coordinates of the center of mass. So m is 1/3, so dividing by 1/3 gives me, in fact, multiplication by 3, which gives me 9/20. So there's where the centroid is. And let's see, I think I got one more example for you. So to calculate center of mass, we just have to, graph what we're looking at carefully and set up the integrals and do them. Here's another one. Center of mass. Sometimes you can use symmetry to shortcut some calculation, right? So if this is constant density, you know the center of mass has got to be where? It's got to be on this dividing line, right? It's got to be in here somewhere. So without any calculation at all, I can tell you that mx is 0. And, all right. So the mass, integral of rho dA, is just integral of rho dA, because I can pull the rho out because it's constant. Now dA is a half disk, so we already know that the area of a circle is pi r squared. We've worked that out, so we might as well use it. And so that's rho over 2 pi r squared. There's my mass. My y moment would be integral of rho over 2, going back to the formulas I stated for you guys back here, using this one, rho over 2 f of x squared minus g of x squared. In the example I was just looking at, g of x is 0, so we just have the f of x squared, essentially. There it is. And squaring that is nice, because then we just get r squared minus x squared. And we can integrate that. And when we do, we get 2/3 r cubed rho. And like I said, x bar is equal to 0 by symmetry, whereas y bar, my over the y moment over m, is this over this. The rows cancel, and we're left with a r. And let's see, is anything else cancel? No, we get 4r over 3 pi is y bar. So there you go. The center of mass is at 0, 4r over 3 pi. So I like that. That's a pretty nice example. See, you don't need to know the density if it's constant. You're like, well, I could have just sent the density equal to 1. I suppose you could have, but it's kind of nice to work out the algebra and see how it cancels, right? So anyway, that's it for this one. And next up, we're doing probability.